All right, we're going to start off this lecture, part three of chapter five, where we were so abruptly cut off the last time. Thank you, Zoom, for that. But we're going to talk about a little bit, so some of the different types of reactions that we are faced with that we can talk about. That your chapter five talks about. Now, I will tell you this: you will be responsible for completing a reaction. If I give you two reactants, whether through naming them, like sodium hydroxide or hydrochloric acid, or give you the molecular formula, you will be required to then tell me the products, and then obviously, just like everything else, to balance the equation. We are going to talk about the first type of equations or reactions that we're going to talk about are precipitation reactions. Um, we left off here talking about that some ionic compounds are insoluble in water, and so this is where we get the idea of a precipitation reaction. And an insoluble precipitate will fall out of solutions. Will fall out of the solution of a chemical reaction. Here's the table. Just be familiar with what this table says. And so, how can we read this table? Well, we read this table by looking at the different types of compounds that are formed by ions. And so if you look on the left, it gives you the ion. So in the first little row there, we're talking about alkali metals, right? Lithium, sodium, potassium. If you see an ionic compound made with one of those, it will always be soluble, right? So if you see NaCl, right, it doesn't matter what is going on, it is always soluble. Same thing with nitrates and acetates. If you see those in a compound, those anions, then you know that it's going to be soluble. Now, chlorine, bromine, and iodine, right, there are some exceptions. And some of those exceptions are, so if you have silver chloride, right, we're going to use silver chloride in a lab to do this type of reaction. This is actually how hard water is softened, if you will, is those ions in the water are removed through salt, through other counter ions, and then the solid is precipitated out. Those things are insoluble. Sulfates, right? Sulfates are soluble unless they pair with these. That's how you read the top part of that box. The bottom part of the box with the hydroxides, those are insoluble except when bound to, let's say hydroxide OH. So if you have sodium hydroxide, right, that is an exception. That is soluble in water. So that's just how, we read that table. As you do your practice, you should have this table with you, just so that you can learn and you can go through this table step by step. I will be giving you this table on an exam, or at least I will let you look at the table on the exam. And so let's talk about the different types of reactions. The first type of reaction is a precipitation reaction. And a precipitation reaction is where a solid forms, right? We call that a precipitate. If you look up in the sky and you see rain or snow or whatever, that is known as precipitation, right? It is a solid rain is liquid, I understand, but it is something that is falling out of something else. And so here what we're looking at is we're having potassium iodide react with lead nitrate, very similar to the reaction that you guys did in the lab, and you get potassium iodide plus lead iodide plus potassium nitrate. Well, now if we were to go to our table, right, lead iodide, so we can look on the third row there where it says when these ions pair with silver, mercury, or lead, they're insoluble. So we know that the lead iodide formed is insoluble. So we're going to look at these. I'm going to give you guys an example of this type of reaction. And what we're going to find out with precipitation reactions is there are different ways to actually represent these reactions. And so one of the ways is the molecular equation that we're familiar with, that I'm going to show you. I'm going to walk you through, especially with these different precipitation reactions, these ionic equations, that what things that we can do to maybe make that, why it makes sense the way that we draw them in the double displacement. At least I'm using words that I'm going to explain in a minute. So that's the molecular equation, and then you get the complete ionic equation, right? That is strong electrolytes. In water, we talked about strong electrolytes will be completely disassociated, and so they don't actually look like the molecular compounds that we draw them at in solution. And then what we're going to do is we're going to talk about a thing called spectator ions, and then how we draw a net ionic equation. I will show you, okay, I will show you what this looks like on the board. I'm going to leave this up just so you can look at it, maybe read it a little bit while I switch the camera over to our board. All right. So looks like our board moved a little bit, but that's okay. So let's go ahead and look at a chemical equation. And so I'm going to start using, describing what this chemical equation is going to be. And so I want you guys to start writing it in the compounds before I start writing it on the board. So we're going to react sodium chloride with silver nitrate, and we're going to get silver chloride plus sodium nitrate. So let's think about this. Sodium chloride, use a different marker, plus silver nitrate. Right? These are going to be aqueous, right? And we have to start putting in states of matter in our chemical reactions now, because it's very important for us to know what we're actually talking about in the different states. And we said that's going to make silver chloride plus sodium nitrate. Okay. So now so when we talk about this, when you're presented with two ionic compounds, right? Metal, nonmetal, metal, nonmetal. When we're presented with two ionic compounds, there's a possibility of a precipitation reaction occurring. And so what we need to do is we need to go to the table and we need to look at what our products are going to be, if they're going to be soluble or not. So if we go to the table, we know anything with an alkali metal is soluble. So we just put aqueous. So then the question is silver chloride soluble or insoluble? And what we actually look at when we look at the table, we know this is a solid, right? So that's going to be a precipitation. When we write this out equation, we then have to balance it. But if we look at it, it's already balanced just as is. So we don't have to do any more steps to balance it. This is known as the molecular equation. I'm just going to put ME for short. Right? The molecular equation is everything in the molecular formula. Now, what we said was for strong electrolytes, which all of these are except for the silver chloride, they will disassociate completely in water. And so what this actually looks like, and I'm not going to put the states of matter, but usually with an ion you put aqueous on it. Just for the time being, I am just going to leave it off. -1 plus 1 plus NO3 minus 1. Now, AgCl will not dissociate because it's a solid. It's insoluble. So we leave that together. And I'm going to do NO3 down here just for the sake of room. And so what you notice, this is known as the complete ionic equation, right? The complete ionic equation is showing everything the way it would look in solution. Everything the way it would look in solution. And so now, let's look. So we talked about spectator ions. So we have the complete ionic equation. Let's draw the net ionic equation. So the net ionic equation is an equation to where we just do we just place what's doing the chemistry. What is actually reacting with each other. And so the way we find out is a spectator ion is one that actually doesn't react with it. It doesn't react, right? It just kind of spectates, just like a spectator in a football game, just sits in the stands and they don't actually play. And so if you see an ion on the reactant side that matches an ion on the product side, that means it doesn't react. And so here what we see is sodium is the same on both sides, and same thing as the nitrate. And so what we get is, and so usually I draw the cation first, aqueous, goes to AgCl, solid, right? And so that is the net ionic equation. And so those are three different ways that we can draw a precipitation reaction. And just depending on what I ask for will determine on which one that you would give me. Now let's look at this. Let's look at another equation. So we have sodium chloride aqueous plus potassium sulfate aqueous. Okay, so now using what we know, what are going to be the products of this reaction? Now let's think about this for just, let's break this down in the simplest of form so we can just look at this. We have AB plus, we usually do CD. Now, A in this example, will it be a cation or an anion? And we can go back to our complete ionic equation to answer that question. A is usually a cation, which means B then is usually an anion. And then C, yep, cation, anion. And so now when we, right, because these are going to dissolve and then reform, when they reform, A can only be with D, and C can only be with B. Now, I mix those around because I usually put, it's just commonplace nomenclature that we always put the cation first. And so let's go ahead and see what we get. So we get sodium sulfate plus potassium chloride. Well, if we remember from our table, both of these are going to be soluble because alkali metals are always soluble when they combine with something. And so now I want you guys to do the complete ionic equation and the net ionic equation, and something weird is going to happen. So go ahead and pause it. You can do it. And then I'm going to give you guys what's weird. So when you do that, what happens? There's nothing left, right? Everything is a spectator ion. There is no reaction. So when we talk about precipitation reactions, it is possible that you might get no reaction. And that's okay, because not everything leads to precipitation. All right, so let's talk about another type of reaction that we're going to cover, that we're going to do in lab. But the way we're going to do it in lab is going to be slightly, we're not actually just going to be looking at the reaction, we're actually going to be calculating something with it. So let's go ahead and flip this around. All right, so that's the precipitation reaction. Second type of reaction is acid and base, right? This is known as a neutralization reaction because the acid neutralizes the base neutralizes the acid. Acids and bases always produce water and salt, right? So H2O, the way I would write H2O for the purposes of this is HOH, because then you know that the H comes from the acid, because remember, acids have H's at the beginning, bases have OHs, hydroxyl groups. And so at least the way that we're going to describe bases and acids. And so that when these dissociate, they're going to dissociate in the hydrogen and the hydroxyl. Those two will combine to form water. Now, some acids lose more than one hydrogen. Things like sulfuric acid, they're known as polyprotic acids, and they can release more than one hydrogen. Now, so if you were to see on an exam or on a quiz, a hydrogen and a hydroxyl group, and they're reacting together, you should know that they're acid-base reactions, and they produce water and salt. Table, in this case, table 5.2 just gives you some strong acids and strong bases. We're going to deal with just strong acids and strong bases later on in Gen Chem 2. If you stay on a ticket, you will learn about different definitions of acids, and you will also learn how to calculate weak acids and weak bases. But for this case, we're not going to worry about it. And so, but what can we do? We can do a titration, right? And we can test how much of an acid or a base that we have by doing what's known as a titration, and calculating what's known as the equivalence point. And the equivalence point is when the number of moles of OH equal the number of moles of hydrogen. We tell this in the lab by an indicator. You can see in the little picture there that has turned pink. And so, but again, the concepts that we use to calculate equivalence point is the same that we have talked about earlier in part number 2, where we talk about, well, how much of this does it take to react with that? So what I'm going to do is I'm going to put a question on the board. I want you guys to work through it. And then I want you guys, if you have any questions about it, just come in and ask me. And then we can work through it together. So let's go ahead. Hopefully the board doesn't fall down this time. Let's go ahead and move my camera. There we go. Like I said, this is a problem with having your board on your couch in your office. So, and I will tell you that to do, and I want you, this acid-base reaction, I would like you to just look at the net ionic equation and the complete ionic equation, because the net ionic equation for acids bases are the same as for any reaction, and it's always H plus OH minus equals H2O liquid. So let's say I want to know the concentration of NaOH in a sample, right? So I have a sample of unknown concentration of NaOH. That's obviously a base. So let's look at what we're gonna, so we have 20 mils of NaOH, right? And we titrate it with, we just go to the lab and we titrate it with 45.7 mils of 0.5 molar H2SO, 4. So sulfuric acid, right? So to the NaOH, we're titrating with sulfuric acid, 45.7 mils, and I'm actually going to draw 2 zeros there so that our answer should be in 3 significant figures. So let's think about this. To solve this problem, what do we need first? Exactly, we need a balanced equation. And so what we have, so I'll work through the equation with you. So we have H2SO4, which is the acid, it's aqueous, plus sodium hydroxide is the base, and that's going to be aqueous. And that's going to lead to, and it doesn't matter that there's 1 or 2 or 3 or 10 protons on here. What are the 2 results of an acid-base reaction? Always. That's right, water, which is H2O, and like I said, I'm going to draw it like this, and you'll see why in a minute, plus we have sodium sulfate. Now, sulfate we know has a -2 charge, and so we need to have Na2SO4. Okay, we're ready to solve it, right? That's right, we now have to balance this equation. So here's why I put water the way I put water. So we have 2 sodium right over here. We have 1 right over here. So to balance this, we're going to put a 2 right there. Well, if we put a 2 right there, remember with the polyatomic ions, we now have 2 OHs. Well, if we have 2 OHs here, we can put a 2 there, and we have now 2 OHs here. So now let's see if we're balanced. We have 2 hydrogens here. We have 2 hydrogens here. We have 2 OHs here. We have 2 OHs here. We have 2 sodium, 1 SO4, 1 SO4. We are completely balanced. This is why balancing polyatomic ions this way makes it just a little bit easier to balance instead of breaking each one up individually. So I'm not going to solve this. I'm going to have you guys work through it because this is very similar to the problem that we worked out in part number 2 of chapter 5. But you tell me, I want you guys to think about what is the first step to solve this problem. That's right, is to find the moles of H2SO4. And then use the molar ratio to convert that over to moles of NaOH. Use the volume and the number of moles to find the molarity, to find the concentration. And there is obviously a caveat in this question. And just to let you guys know, it has to do with the volume. So just be aware of your units and beware of the units of the derived unit that we're using with molarity. All right. That's not what I want. So let's go ahead and we're going to look at, so this is titration. You would do this if you were to take Gen Chem 2 in the lab. You would do this in lab. And so you would actually be able to see what that would look like. You've already done this in lab. And so we're just going to briefly touch on it. And that is gas evolution, right? And that there's some reactions where a gas is let out. And so this is two aqueous solutions mix, and what you do is you get bubbles. As you can see, if you see CO3 or SO3 or H2SO3, H2CO3 in a chemical reaction, you know a gas is going to be evolved. I don't really focus much on gas evolution reactions. Just be aware that they exist because we need them for lab, and you guys have already worked through them for lab, seeing those intermediates. And so what we're going to do is I'm going to go ahead and I think I'm going to just stop chapter 5 part 3 here, and we're going to do chapter 5 part 4 briefly with reduction oxidation reactions, because we need to know what those are and maybe walk through them just a little bit slower than we might be able to rushing through the end of this video.